Welcome to This Explainer. Okay, today we're uncovering a pretty fascinating mystery straight from the manufacturing shop floor. When you look at a machined cylinder or drilled bore, it usually looks perfectly round, right? Well, actually, scratch that. Perfectly round machine parts literally do not exist. In reality, they're plagued by these hidden geometric errors. And those errors, they can absolutely destroy the performance of a rotating machine element. We're talking vibration, noise, premature wear, the whole shebang. So today, we're going to uncover these hidden pitfalls. We'll look at why our standard go-to measurement tools might actually be lying to us, and we'll explore the precise mechanical solutions we can use to fix all of this. All right, so here is our roadmap for today. First, we'll look at the illusion of perfect roundness. Second, we're diving into the V-block measurement trap. Third, fixing errors during machining. Fourth, honing as the ultimate finish. And finally, preventing chatter with tool geometry. Let's get into it.
Section 1. The illusion of perfect roundness. Let's start by totally shattering the idea that any hole, cylinder, or sphere comes off the lathe or grinder perfectly symmetrical. Just no way. Technically speaking, out of roundness, or roundness error, is defined as the radial deviation between the minimum inscribing circle and the maximum inscribing circle that contains the profile of your surface. But here's the thing. In practice, this deviation isn't just random, messy roughness. Because of the incredible stress exerted on a part during turning or grinding, these errors actually take on very specific geometric patterns. They show up as peak and valley structures on the surface, and machinists refer to these as lobes.
And this brilliantly illustrates what we're talking about. When you exaggerate it, lobing takes on some really fascinating geometries. You might see simple ovality, which is essentially a two-lobed shape. Or you might see a distinct three-lobed shape, which is notoriously common with centerless ground components. Then, of course, you have multi-lobed forms. Think about it. If you were to try and fit a multi-lobed shaft into a perfectly round ring gauge, you can instantly see how those peaks and valleys would completely ruin the fit and function of a bearing or a seal. It's like trying to fit a square peg in a round hole just on a microscale.
Now, the way you clamped the workpiece, that is absolutely one of the biggest culprits here. When a rod is being turned, it's usually held tight by a chuck. A standard 3-jaw chuck puts stress on 3 very specific points of the cylinder. So as the cutting tool applies pressure against those unsupported gaps, it inevitably produces 3 lobes. It's just physics. Interestingly, though, this error actually reduces when you machine closer to the tailstock, because the tailstock supports the workpiece completely around its circumference. Now, you might be thinking, okay, I'll just switch to a 4-jaw chuck. Well, that does eliminate the positional error along the length of the part, but it doesn't cure the lobing. You simply end up producing 4 lobes instead.
Section 2. The V-block measurement track.
So you've got a lobed part, and you send it over to quality control. But here is where it gets really interesting. Standard metrology has a massive blind spot. A super common way to check for roundness is to just plop a shaft into a standard 90-degree V-block and rotate it under a dial indicator. But here's the trap. Supporting a lobed part in a standard 90-degree V-block will actually conceal roundness errors. Plain ovality, or any even number of lobes, might rotate in that V-block without moving the dial indicator much at all. And for odd numbers of lobes, a standard 90-degree block is completely inadequate. To measure the exact amount of lobing, you literally must use a V-block with a specific included angle that is mathematically related to the number of lobes on the part.
To put that into perspective, look at this data straight from the machinery's handbook. If you have a 3-lobe form, you shouldn't use a 90-degree V-block at all. You actually need a 60-degree included angle V-block. And the really crazy part is what they call the exaggeration factor. Using a V-block for parts with odd numbers of lobes gives you exaggerated readings. For example, if you put a 3-lobe part in the correct 60-degree block, the reading bouncing back on your dial indicator is actually 3 times larger than the true out-of-roundness value. You literally have to do the math to find the real error. It's wild.
Which brings us to a really crucial takeaway for today. Just because you measured a part in a standard V-block and the needle didn't move, absolutely does not mean it's actually round. You might just have an even number of lobes perfectly hiding in plain sight.
Section 3. Fixing errors during machining.
Okay, so once we realize the part isn't round, and we've managed to actually measure it correctly, how do CNC operators tackle this problem right at the machine? Well, it turns out turning parameters have a massive influence on roundness. Research shows that feed rate and depth of cut have the most significant effect on roundness error, way more than spindle speed. If you want to shrink those lobes down, the optimal adjustment is to use a lower feed rate paired with a higher depth of cut. And like we mentioned earlier, if you're stuck using a 3-jaw chuck, try to design your operation so the most critical roundness tolerances are machined closer to the tailstock where the part is heavily supported.
Section 4. Honning, the ultimate finish. But let's be real, sometimes machining adjustments just aren't enough. When you need absolute perfection in a bore, you call in the superhero of surface finishing processes. Listen to this quote from the experts at Nagel USA. They note that honing can efficiently correct bore geometry distortion from upstream machining processes, welding, or heat treating. It is the ultimate corrective measure for all the clamping distortion, the lobing, and the tool marks we were just talking about. Let's look at why it works. Unlike standard grinding, honing builds a better part by using abrasive stones that expand outward under controlled pressure while simultaneously rotating and moving up and down in a reciprocating motion. This unique, compound mechanical motion allows it to truly true up a cylinder. It practically erases waviness, barrel forms, and out-of-roundness. Plus, that back-and-forth motion creates this signature microscopic crosshatch pattern on the surface. And in applications like engine blocks or hydraulic cylinders, that crosshatch is absolutely essential because it actually acts like tiny reservoirs to retain oil, vastly improving your lubrication and sealing. It's a real game changer.
Section 5. Preventing chatter with tool geometry.
So, we've talked about measuring errors, adjusting machine feeds, and honing them away entirely. But can we prevent these issues at the source before they even start? Yes, for sure. And we do it by paying incredibly close attention to tool geometry. One of the most critical factors here is the lead angle. Now keep in mind, the lead angle is not an angle ground into the tool itself, it's a tool setting angle. It's the angle bounded by the side cutting edge and a plane perpendicular to the direction of the feed travel. Setting this angle correctly has a massive, massive influence on how the tool performs and just how much stress it puts into the workpiece.
So what does this all mean for us? Well, it's a huge trade-off. As you increase the lead angle, you thin out the chips. This acts almost like increasing the depth of cut, which is fantastic because it increases tool life and allows for faster production. So generally, you want that lead angle as large as possible, but a high lead angle pushes a lot of radial force directly into the part, which greatly increases your risk of chatter. You know, that destructive, screaming, vibrating resonance. On the flip side, if you drop to a low lead angle, you can often instantly cure chatter. For long, slender shafts or boring bars that are highly prone to vibrating, keeping that lead angle small is completely essential.
In fact, sometimes you literally have to take it to the extreme. If you're turning a really long, slender workpiece that is just screaming with chatter, setting up a tool with a 0-degree lead angle might just be the exact geometry tweak that saves your part. It totally eliminates those geometry-ruining vibrations. The other vital piece of geometry is the nose radius of the cutting tool. You know, the literal tip doing the cutting. A sharp point is going to leave a terrible finish, so a radius is required. The golden rule here? It's a balancing act. Step 1. Make the radius as large as possible. Why? Because a larger radius overlaps its previous cuts, smoothing out the peaks and valleys for a beautiful finish, all while allowing faster feed rates. Step 2. Closely monitor the machine. Because just like the lead angle, a radius that is too large increases the tendency for chatter. And step 3, if chatter does occur, well, you've found the physical limit of your setup, and that radius must be swapped for a smaller one immediately. So we've seen that chucks literally squeeze parts into lobes, V-blocks can completely hide the truth from us, and our cutting tools are just constantly walking this tightrope between maximum efficiency and destructive chatter. It really is a delicate dance of precision and physics. Which leaves us with this final thought. If perfectly round truly doesn't exist in the physical world, how close are you willing to get before the machine fights back? Thank you so much for joining me for this explainer. I really hope this helps you look at manufacturing precision in a whole new light.